press pause and answer the question.
So now we're talking about this distance between Mars and the Earth and our spaceship that's going to get us there, but we're going to look at it through the lens of scientific notation. And scientific notation is pretty handy if we're talking about really big numbers. And these are starting to approach the kind of really big numbers where scientific notation starts to make much more sense than actually writing out the numbers. So again, we're trying to find out how many hours. This time it's how many hours. Written in scientific notation, would it take for people to get from Earth to Mars? And this is the correct answer. It's 3.9 times 10 to the 3. Let's go ahead and work this out. So we have 2.25 times 10 to the 8th kilometers. That's given. And we want to figure out how many hours that is. And how many kilometers per hour? Well, it's 5.8 times 10 to the 4th kilometers for each hour. So we're going to have to put kilometers down here and hours up here. So then we know we have to take 2.25 times 10 to the 8th divided by 5.8 times 10 to the 4th. And it could be that your calculator will take those scientific notations and it will figure it out for you, and that's great. In the absence of that, what we can do is we can say, okay, we have 2.25 times 10 to the 8th in the numerator, and we have 5.8 times 10 to the 4th in the denominator. And so we can take 2.25 divided by 5.8, and that gives us 0.39. And we have 10 to the 8th divided by 10 to the 4th. And so we know 10 to the 8th divided by 10 to the 4th is just 8 minus 4, 10 to the 4th. Our answer is 0.39 times 10 to the 4th, but that's not our answer. That's this number right here, but that's not the correct answer. The correct answer is this number here, 3.9 times 10 to the 3rd. Now granted, this number and this number are the same, but only this one is in proper scientific notation. Now, is that just someone being picky? No, not really. There's lots of rules that are kind of stupid, but this one actually makes sense. Let's go into it. So why do we deal with that? Well, why even deal with scientific notation? Because I think most of our hearts kind of sink a little bit when we see that scientific notation show up, because it's hard to get our heads around those numbers and what they mean. So what does it mean? If you have 10 to the 7th, well, that's 10 times 10 to the 6th. And 10 to the 7th is 100 times 10 to the 5th, and 1,000 times 10 to the 4th, and 10,000 times 10 cubed, and so forth. So if Mars is 2.25 times 10 to the 8th kilometers per our assignment, our problem, our item number that we just looked at, then that means we're going to move our decimal point 8 times to the right, and we're going to backfill with zeros. So that 2.25, we'll move that decimal point 1, 2, 3, 4, 5, 6, 7, 8 times. We'll put our commas in so it's clean, and we get 225 million kilometers. Now, to put that in perspective, that's 2 adjacent planets. The distance between 2 adjacent galaxies may be as high as 1.22 times 10 to the 23rd kilometers. Now, what does that mean? We have to move that 1, 2, 3, 4, all the way to 23 times, and we get a number that looks like this. And the numbers, they start to get too large to really work with. It's really hard to get our heads around that. And also, you notice the numbers in the middle really don't matter. And they don't. I mean, when you first start looking at scientific notation, you kind of focus on these numbers. But after you get used to looking at them, you realize that the real action is in these numbers here. So if 2 planets is 10 to the 8th and 2 galaxies is 10 to the 23rd, that actually tells me a lot more than anything about this number and this number, because those almost don't matter. If we look at these 2 numbers, the 10 to the 23rd relative to the 10 to the 8th, and then you take 1,000,000 of that distance, and then you take 1,000,000 of that new distance, that's 1,000,000 of the first distance, and then you take 1,000 of those millionth distance, that's the kind of distances we're talking about. So the fact that one is double the other, really, it sounds like a lot, but it's not that important compared to the number of zeros that you have at the end. It's really all about the exponent. Now it goes the other way too. Negative exponents go the other way. So the sound pressure of a whisper that you can barely hear, just at the threshold of hearing, the sound pressure of that in pounds per square inch is 0.000000003 psi. So 0. And then 8 zeros and then a 3. Anything less sound pressure than that, we can't hear it. And the sound pressure of a jet engine at close range, kind of the threshold where our ears start to hurt, is at 0.03 psi. Now, there's all kinds of problems with writing those numbers. First of all, they're clumsy. That's a whole bunch of numbers. Second of all, they both look really small, but one of them is 10 million times the other one. So this one is 10 million times this one. And we need a way to express that. So we can write this one as 3 times 10 to the negative ninth. So now instead of moving the decimal point to the right, we can move the decimal point to the left. So we have 3, and then we're going to go 9 times over here to the left. And this one here can be written as 3 times 10 to the negative 2. So we 3, and then we go 1, 2. And so we can compare them, and we can say, okay, there's a difference of 7 zeros. And we know 7 zeros is 10 million. So we can look at, this is negative 9, this is negative 2. There's a difference of 7 zeros. That means that in sound pressure, the threshold of pain is 10 million times the sound pressure of perceptibility. But you'll notice we can also write this one as 0.3 times 10 to the negative 8th, right? Because 3 times 10 to the ninth is the same as 0.3 times 10 to the negative 8th. And we can write this as 3 times 10 to the negative 2. We can write it as 30 times 10 to the negative 3. But when we do that, you see when we look at the exponents, now it's only 5 digits, 5 zeros to look at. And so we're really not comparing apples to apples because this number here is below 1 and this number here is greater than 10. So we want these numbers to be bigger than 1 and less than 10. That way we know we're really comparing apples to apples. So let's do the actual problem. All right, so you'll remember that we left off where I got sidetracked about the importance of playing by the rules when it comes to scientific notation. We were talking about these two numbers, 0.39 times 10 to the fourth, and how it's the same as 3.9 times 10 to the third. And how do we know? Let's say that we know that this number here has to be between 1 and 10. So then we know that it does have to be 3.9. That makes sense. And how do we know we don't go to 10 to the fifth? How can we go to 10 to the third? What's happening here is we're multiplying this number by 10 to get the 3.9. So then once we do that, our number is too big by a factor of 10, so we have to take 1 10 off of this, and that has to be 10 to the 3 instead of 10 to the 4. And so there's your answer, 3.9 times 10 cubed.